Hey everybody, this is what we call in science a cucumber. Actually, he's so small, I'm going to go ahead and say he's a cute-cumber. So he's going to become a pickle though, as I put him in this brine. I'm going to submerge him in the brine, and now on his way to a state which we call in science deliciousness, some osmosis is going to occur, because what's in there is a brine of about half vinegar, half water, bunch of sugar, a little bit of salt. And so what's going to happen through his membrane is some osmosis. So we're going to talk about osmosis today, but first we have some unfinished business with freezing point depression and boiling point elevation. Let's go to work. Welcome back, everybody. Before we talk about pickles, we got to do a couple problems to polish our skills in the area of using freezing point depression or boiling point elevation to calculate important things like, how do we figure out how many grams per mole something is? So for example, we got this compound and they say, what's the formula? But the way that they used to figure out the molecular weights of things before the age of the fancy schmancy instrumentation that we have now, they would put a known amount into a solvent and see how much it depressed the freezing point or elevated the boiling point. And so we have this compound that's organic. Now that means that usually means it's non-polar because it's carbon based, and it has a composition of that much carbon and that much hydrogen. And we dissolved 0.090 grams of the compound in camphor, which by the way is another organic substance which is mostly carbon, hydrogen, just got one oxygen. I think it's C10H16O is its formula. So pretty non-polar. A little bit of side note, like dissolves like. Non-polar dissolves non-polar. And so this will readily dissolve in camphor, and then, oh, bang, here I see something. I see melting point, and I see two melting points, and so what I can do to get started is I can write down our freezing point depression equation, which is delta TF equals KF, which by the way they gave us, look at bang. So you're kind of reading these here, KF, delta T, and you realize that you've got 2 out of 3 variables, so the only thing I don't have is M. And to be honest with you, I'm just going to keep going and calculating what's missing. So they gave us a K. By the way, do you notice how huge that K is compared to the one we did of water yesterday? Last time, I should say. Water's K is 1.86, and camphor's K, its freezing point depression constant, is 38. And so that's another reason that they would use these organic substances, is they have huge Ks which make big delta Ts easy to measure. See, that's a delta T at 20 degrees. I'm going to go ahead and say that. Negative 20 degrees C. And I got a K. So quick rearranging, I'm just going to go ahead and solve for M, since it's the only thing missing. Sometimes you don't even have to know the end game. You just got to solve for what you can. And right now, I got a delta T, I got a K, and I can find the molality. So let's do that. It'd be negative 20. Okay, right, there's a negative in the formula. So if I had continued with negative 20, then I would have had 2 negatives in there. So let's say that this is now negative in there somewhere. But I'm just going to get rid of it because molality can't be negative anyhow. So I'm going to go 20 degrees C divided by 37.7 degrees C per molality unit. The degrees C cancel, and I have units of molality, 1 over molality. Now here's the trick. You got to remember 0.5305. what molality means. So let's reflect on that. Now I know what the molality of that solution is. Part of the molality is moles. If I knew how many kilograms I dissolved it in, which I do, I can find moles. If I know how many grams I have of it dissolved, I could find grams divided by moles. So the next step, and what is usually the next step in these problems, is you use the molality to find moles. But remember, these little abbreviations are quite dangerous because you're saying like to yourself, oh, I see a lot of my students make the mistake of saying M is moles. Nope. M is moles, compound, per kilogram. Camphor is the solvent. And now I have 1.10 grams, and divided by 1,000 is 0. This right here, 0.0011 kilograms. I'm going to end up multiplying by that, and that is going to give me my moles. So 0.0, got to watch it I don't miscopy. And I'm going to have a relatively small number of moles, but that's okay. It's only, 0.090 grams or something. So 0.5305 times 0.0011. And then I've got, let's go ahead and convert that to scientific notation so I don't miscopy zeros. 5.8355 times 10 to the minus 4 moles. Kilograms have canceled. I'm kind of one step away. What I'm going to do next is I'm going to take the grams and divide it by moles. Then, a lot of times you're done. In this particular case, they want to know, hey, what's the formula? And then we got one extra step. So I'm going to go ahead and take 0.090 grams. And then you're thinking, man, I haven't used that number. It seems awful lonely. Well, now we're using it. It's getting to its chance to shine. That number was sitting there like, put me in the game, coach. And now it's the closer of numbers. I don't know, I might have drank too much coffee. So then times 0.09, it is 1.54 times 10 to the 2, or what we normally call 154 grams per mole. Didn't answer the question yet. What's its formula? It's CXH something. Why? And I could just slap a whole bunch of things together and find out what it is. But you know what I could do? I could then say, well, what if I had multiplied my grams per mole times the percentage? So let's say I have, assume 1 mole. I got 154 grams of this stuff. Fair enough? I'm going to go ahead and say that I got it. Now it's back to Gen Chem 1. This is why I picked this one out, folks. This is a hard one. Because normally you're done right here. But let's go the extra mile here. Let's go ahead and take 154 grams times 0.9346. Let's take 154 grams. Now these are the percentages that were given in the beginning of the problem. So let's go ahead and let's just now figure this part out, where we go and take the amount of each that's carbon. So 154 times 0.9346. So I've got 144 grams of carbon. And then the rest, which it better be 10, but I'll double check. You know, they should all add up to 154 grams. So 154 times 0.0. This is a good way to find out. See, I just typed something in wrong. These both should add up to 154. So the 144. So this better be, when I multiply 154 times 0.0654, it is just about 10 grams. Now, of course, that's not how you get a formula. I've got to divide by the molar mass, so 12 grams, 1 mole. Hydrogens are so nice. 1 gram, 1 mole. Notice I didn't even do 12.01 and 1 because I'm going to come up with a round number. So that is 10 moles H. And then 144 divided by 12 is, well, 12. 12 moles C. So the formula is C12H10. And then does that weigh 154 grams? Yeah, and then you know what you could do if you had oodles of time. You could plug it back in. You could say, what if I had 0.090 grams of that? You could find out how many moles that is. And you could divide it by 0.0011 kilograms and plug it back through the equation. And then find out what your delta T should be about 20 degrees if you care to do such a thing. I mean, we just spent 10 minutes doing that problem. I don't think you really got much more time other than that. But that is the way that people deduced the formula of compounds back in the old school days when science was done by, you know, guys in white wigs and stuff. So that is a very tough problem. That's why I picked it out of the book to do as an example. Got one more, and then we're going to move on to osmosis, and we're getting towards the tail end of chapter 11, which is a difficult chapter, as you can tell. Let's do another one. All right. So, folks, this one's a little spicy. I'm trying, at least I'm saying it is, to make sure you're interested. This one's a salt of an alkali metal and then a fluoride. Okay, alkali metals group 1, so this is going to be something XF, and it's going to be a 1-to-1 ratio because that's how the periodic table works. This is going to be a positive 1 ion. So we're talking, this is going to be lithium fluoride, sodium fluoride, potassium fluoride, rubidium fluoride. And so there we go. Let's keep reading. 4 grams of the salt. All right, it sounds like what we had last time. There's some number that's going to wait till the end. Dissolved in 100 grams water, let's call that 0.100 kilograms, produces a solution that freezes at, now it's water. Hey, that's not only our freezing point, that is our delta T. Because we subtract that from, that's from 0. So when you have a water example with freezing point, it's really nice because the temperature is the delta T because the pure stuff, it melts at 0. So cool. Now here's the thing. I waited till now and I have to tell you a little bit of truth about the freezing point depression or the boiling point elevation equations. And this is the I. There's a little addition in there that I didn't bother you with till now because we didn't need it till now. Right before the K, which by the way, let's all assume you know how to look this up in the table. This is 1.86 degrees C, just like it was in the last example, the last problem. The negative sign's still there. What's up with I? I is something called a Vant Hoff factor. The Vant Hoff factor, scientists found they were puzzled by the fact that something like a salt would not behave like one particle. And you know this, folks. You know how electrolytes work. If you were to go and take, this is an integer in theory. And so what would happen is if you were to go and take a sugar, and dissolve it in water, you would find that behaves like a single solitary particle. I would be 1. Now let's say I take sodium fluoride. I don't know if that's the answer. Maybe it would be. And then it's better to be lucky than be good. I don't know if it's sodium or lithium. You remember from Gen Chem 1 that is really not NaF. That is Na plus dissociated and F minus. That behaves like, if you dissolved a mole per kilogram, it's going to behave like 2 moles per kilogram, and that is an I of 2. If you had something like calcium chloride, that would make calcium chloride aqueous, but we all remember back from Gen Chem 1 that is really a Ca2 plus and 2 Cl minuses. That is a theoretical I of 3. Now it gets even more spicy, because what happens is in a solution, these things aren't perfectly not wanting to have anything to do with each other. So it's kind of like it's complicated. It's one of those relationships where it's complicated. And you're like, hey, is sodium and fluoride, are they together or not? And it's kind of like, no, it's a little bit in between. Because what happens is I equals 2, this is theoretical. But in a solution, they're actually not going to behave totally independent. They have once in a while, they'll be loosely associated with each other. They call this ion pairing. So you know what happens? It's more like 9 actual. Could be 1.8. Double check me. It's in the textbook, I'm sure. So what we got going on, folks, is we're going to go and have to stick an I of 2 in there, because I'm sure this is the world of the homework problems where everything's theoretical. So when I go ahead and do this, I am going to have to include I. So it's delta T F equals minus I K F M. And then what we're going to do is we're going to plug in everything we know. I'm going to go ahead and say, since I know I equals 2, because they gave us a hint. Since I've looked up, this is 1.86 degrees Celsius per molality unit. And since they gave us minus 1.4 degrees C, I'm going to go ahead and write off screen. Completely right while I'm off screen. I'm going to go ahead and solve for still what I know how to solve for, which is the molality. Fair enough? So I'm going to go ahead and solve for M. That is delta TF over minus I and then KF. Those negative signs will cancel out. And so let's plug it in there. Minus 1.4 degrees C minus 1.86 degrees C per molality unit. Very similar to the last one, we will have units of molality when we get done with this. So let's go ahead and I'm going to go like this. I'm going to get rid of these. Can I do that? I just did that. 1.4 divided by 2 divided by 1.86. This is 0.3763 M. Got to remember what M means. That's moles per kilogram, and I got 1/10 of a kilogram. So I'm going to go ahead and say 0.3763. This ends up being very much like the last one. And then so times 0.100 kilograms. So hey, pretty much do it in my head, 3763 moles. Now we're getting to the end of the puzzle. I had 4 grams of it. That was given. And there's that lonely number of grams that were dissolved. So I'm going to go ahead and say 4 grams divided by 0.03763 moles. Let's see what that is. And that is, whoopsie, I hit the wrong button. Divided by 0.03763. 106.3 grams per mole. Oh boy. Let's go and think about the alkali metals combined with a fluoride. So, LiF. I'm not going to even do, I'm just going to go run through them. Let's go down NaCl. Not NaCl, Mike. NaF. KF. What would lithium fluoride be? Well, fluorides are 19. And lithium in the periodic table is 6.94. So I've got, this would be plus 19, sorry. This would be 26 grams per mole. What would a sodium fluoride be? Sodiums are 23 plus 19. This would be 42 grams per mole. Oh my goodness. RBF. He's like, this problem has RBF. So we got 19. Okay, potassiums are 40. So this would be 59 grams per mole. Potassium's been about 40. This would be 59 grams per mole. I was wrong. I guessed it might be NaF. Oh my goodness, folks. I got to go find out what a rubidium weighs. Oh boy, folks. I had to get my periodic table out there because we usually don't get down as far as rubidium. But a rubidium is 85.5. And so if we went 85.5 plus 19 for a fluorine, then this would be 104.5 grams per mole. I went as far as to go look up cesium too, because cesium, then you got francium, but I feel good about, the outcome here because I think cesium is too heavy. So this would be 151.9. And I'm glad this came up. You'd be like, geez, it's not 106. Okay. But it's close. And there's error. I rounded a few numbers there. They gave us very round numbers. Maybe the delta T was a little bit bigger than what it should have been. Or, geez, I had to trace it all the way through. Should it be bigger or smaller? But that is a bear of a problem, folks. And we did, hey, I like doing the bear of problems because the ones that are hard, because you don't get sharp teeth eating oatmeal. But boy, that was thinking, and you could say that's not realistic, rubidium fluoride. Yeah, I know, rubidium is pretty obscure. So is cesium. By the way, cesium costs more than gold per ounce. It's super duper obscure and hard to purify. So let's talk about pickles. All right, folks, this is where we started our journey today. Is I showed you I do grow my own cucumbers, and I picked that one prematurely because I wanted to show you the process of a cucumber becoming a pickle. So what you do is you take salty, sugary brine. Let's make him as small as he was. He kind of looked like this. There's our cucumber. And so this is salty brine. I like to put hot peppers in. I grow hot peppers too. I sound like I'm bragging, but I am. And then so, you go and let them sit for, actually, ideally more than 2 days. But and by the way, making your own pickles, good for your gut. Fermented food's supposed to be good for your gut, but I digress. Now what's going to happen is osmosis is the movement of water across a semi-permeable membrane. And you know what? Organisms have semi-permeable membranes everywhere. But it's the movement of water from where I'm going to go ahead and underline it, is in, it's really kind of like diffusion, high concentration, to where I'm going to go ahead and write it underlined again, is in low concentration. This makes sense to you, right? Nature wants to even things out. So, there's a lot more water in those pickles. Or, sorry, it's not a pickle yet. There's a lot more water in that cucumber than is in the brine. And so you will find that there is going to be, across a semi-permeable membrane, which only lets waters go through. Waters are pretty small, folks. So the water is going to come out, and that cucumber is going to look shriveled. And if you go in the grocery store and you look at a pickle, it looks a lot more shriveled than a nice fresh cucumber that comes out and it's all kind of round and plump. And so you're going to be sucking the water out of that thing. I suppose if you were to put a pickle in deionized water, the water would go the other way, because there'd be more water outside than in. And so, you know, there's all sorts of terms for these solutions. You know, hypertonic means that, you know, that the concentration is higher, and isotonic means the same, and hypotonic means lower. But bottom line is there's going to be a pressure. And the pressure here has a symbol called pi. And therefore what happens is, if you were to measure that pressure, it is proportional to the concentration and then times a constant. But that's let's just like freezing point, depression, and boiling point elevation. If I were to say double the concentration in that salty brine, that pi would double that pressure. And that's the pressure of water molecules pushing through the membrane. And if you were to pour a bunch of water in there, you'd cut the concentration in half, and the osmotic pressure would then decrease proportionately. And so that's osmosis, and that could be used to calculate the molar mass of something, because if you find the concentration, you could find the number of moles, and you can find grams per mole. But we're not going to do that today. I've already used you enough and thrown enough numbers at you with those two nasty, nasty problems. So next time, we will talk about what is a solution. What is something solution like? Like, is milk a solution? Turns out no, it's a suspension. Ooh. So we will talk about that next time. Until then, enjoy yourselves and stay healthy and safe. Toodaloo!